Good afternoon, everyone. Welcome to our next a16z Crypto Research Seminar. Very pleased to introduce Kartik Nayak, who got his PhD from Maryland, is now an associate tenured professor at Duke University, also an advisor for Espresso Systems, which is very cool. He's done sort of work all across security, applied cryptography, consensus, lots of areas super relevant to blockchain protocols. And today we get the latest update on the progress on DAG-based protocols. So, Kartik.
Thank you so much, Tim, for the kind introduction, and thank you so much for inviting me. So I'm very, very excited to be here. So I would mention that this is like the first time ever that one of my PhD advisors, one of my postdoc advisors, and my closest collaborator are in the same room for 5 days in a row. So
no, there's also the first time that the Q&A session already started before your talk.
Yes, Elaine started asking me questions before my talk. Yes. So I'm very excited about this topic. I'm going to talk about DAG-based protocols. So this is something that where there has been a lot of excitement over the last 5 years. I'm going to present my view and the progress that I have seen, the progress that I have helped made in the recent past. So to be frank, until maybe mid to late 2023, I entirely ignored the space, and then I started working on the space. So during my talk, you'll see some degree of chronology in terms of how improvements were made in my line of work. So what is the problem of interest over here? It's state machine replication, where you have a group of parties that agree on a common sequence of transactions submitted by external clients. And you want to achieve this even if some of these parties are faulty. Okay, so the party over here with the red cross, that is a faulty party, and you still want the other parties to agree with each other. So you have transactions coming in one at a time. These parties run some consensus protocol, and they produce the next block. And they keep doing this over and over again. There are two key properties that you want. The first one is safety, which says that any two non-faulty parties do not learn a different sequence of transactions. And the second is liveness, which says that a transaction that is proposed by a client will eventually be executed by every non-faulty party. So generally, you want safety and liveness, even when some of these parties may be faulty, arbitrarily faulty. We're going to call them Byzantine faults. So T out of n of these parties are Byzantine faulty. And this should hold under different network conditions that the protocol assumes. And throughout, I'm going to assume partial synchrony as the underlying network condition. Okay? And under partial synchrony, it is known that you cannot tolerate more than T. So T less than n over 3 is a bound of the number of faults you can tolerate. So there are two key metrics that we typically optimize. One is latency, and the second is communication complexity. So latency is the time to commit a client transaction. Okay, a transaction arrives, these parties agree on it, and the client gets a response. And the total time it takes, you can measure it in number of rounds, number of deltas, wall clock time. So it is the latency to commit a client transaction. And the second is communication complexity. It is the number of bits communicated by honest parties or non-faulty parties. So if you look back at the history, most of the protocols under partial synchrony used a very specific way of doing consensus. And we colloquially, we call them leader-based protocols. Over here, you would have a designated leader who is responsible for proposing blocks of transactions and getting all parties to agree on them. The idea is that if the leader is honest, after GST, that is after the network is synchronous, you'll have both safety and liveness. But if the leader is Byzantine, you can never expect liveness, but you will ensure that the protocol ensures that a Byzantine leader cannot break safety. The hope is that eventually you will have an honest leader, and eventually the network is going to be synchronous. So eventually you'll make progress and you'll maintain safety at all times. Many protocols follow this approach. I have listed some of them over here: PBFT, Tendermint, Hot Stuff Pala, Hot Stuff 2. There are many others. And if I look at what these protocols do with respect to these two metrics, they actually give you ideal latency, ideal communication complexity. So there is PBFT that already gives you ideal latency of 3 rounds. And there's Hot Stuff that already gives you ideal communication complexity. So a natural question is, aren't we already done? The problem, though, is that we typically relate communication complexity or low communication complexity with high throughput. And that may or may not be true. In particular, with a leader-based protocol, your leader can be a bottleneck. So there are two key ways in which a leader can be a bottleneck. One is there is unequal scheduling of work in a typical leader-based protocol. For instance, imagine a leader is sending a 1 megabyte block to 1,000 parties. Then the leader is actually sending 1 gigabyte worth of information. whereas each of the receiving parties are only receiving 1 megabyte worth of information. So if you think of it from a network standpoint, the leader is doing a lot more work than any of the recipients. And second, typically in these protocols, if a leader fails for whatever reason, there is no progress whatsoever, and this can reduce throughput. Because of these reasons, despite having good communication complexity, we may or may not have good throughput. So the problems I'm raising over here are very well known, and there are approaches to actually addressing this. There is a line of work on extension protocols where you can extend from a 1-bit consensus to an L-bit consensus protocol for an arbitrary value of L. And the key idea over here in improving communication complexity, or the amount of work the leader has to do, is to rely on erasure coding techniques. So there is another line of work on data availability oracles, which in spirit kind of does something similar. It tries to achieve balanced communication. There are other techniques, systems level optimizations like Narwhal, where you can separate transaction dissemination from consensus. So all of these lines of work can actually help improve throughput.
So like Solana's turbine, I should think about it sort of in those top 2 bullets? Or?
Yes, exactly.
Okay.
What do DAG-based protocols give you? I would argue that they would give me similar properties in perhaps a slightly more natural way. Because in a very natural fashion, in DAG-based protocols, every party performs a similar amount of work at all points of time. In a sense, because everyone is doing the same amount of work at all points of time, fundamentally it solves the unequal scheduling problem. And second, the advantage is that your DAG construction, it does not depend on a leader. So you'll keep creating your DAG even when a leader fails, and whenever a leader comes in afterwards, you can commit everything that has happened in the past. This, though, comes at the cost of a high communication complexity, which is typically incurred by these protocols. I will mention that whatever these protocols do, it is not the case that prior protocols could not do. It is just that these protocols kind of achieve them in perhaps a more natural fashion. So if you look at prior DAG-based protocols, they improved throughput at the expense of communication complexity for moderately sized settings, okay, for something like n equals 100. But they actually did not give you ideal latency. And this is our first foray in terms of trying to work on DAG-based protocols, where we wanted to improve the latency of DAG-based protocols. And this is a work called Sailfish, which is published in S&P 2025. Let me talk about the core protocol that we have. It's the most natural protocol, at least that I can think of, and perhaps you can think of as well. So over here, I'm describing this for n equals 4 parties. So every party maintains a DAG of blocks proposed by parties, so 1 row for each party. And the protocol progresses in rounds. So this is the frontier of the DAG at the end of round r minus 1. When we move to the next round, what we require is that a vertex of round r, this is a vertex that is proposed by the first party P1. So vertex of round r points to 2t plus 1 vertices delivered from round r minus 1. Okay? So every such vertex has this constraint. So over here, when I say a vertex is delivered, I mean it in a very specific sense. So it is output by a reliable broadcast protocol. Okay? And this gives me 2 key properties. So the first property is non-equivocation, which basically says that if some party Pi has sent me a block in some round r, for any other honest party, they would deliver the same block r, or they will not deliver a different block for the same party in the same round. Okay? So the second property I get because of an RBC is totality. And totality says that if an honest party delivers a block, all other honest parties will deliver that block as well eventually. So due to this, every honest party will eventually build the same DAG.
In the end, is it required to linearize the DAG, or it's not required to linearize?
So you linearize the DAG. So in the end, you have a chain.
So is there any requirement on how fast these blocks arrive? Because if people have to see different subgraphs of the same graph, then the linearization will be different.
That's a good question. So over here, every honest party will eventually build the same DAG. But to answer Elaine's question, that is exactly where we need consensus. Okay? So what you can have is that at any point in time, The view of party Pi looks like the following, where you have in round R, you have delivered all vertices, but not the last vertex proposed by the fourth party. But for some other party Pk, they may have a different view where they have not delivered, let's say, the third vertex. And to agree on which of these vertices are delivered at any given time, this is where these protocols require agreement. So how do you achieve this? You use leaders. Okay? So every round is going to have a leader, so it's marked with the crown. The idea is that we will commit leader vertices, and based on committing leader vertices, we'll order all other vertices. Okay? So if I have to commit leader vertices, what we do is that we parties prioritize pointing to the leader vertex. For example, if I want to commit the leader of round R, everyone in round R plus 1, they'll prioritize pointing to the leader of round R. So I can only do so until a given time, because if the leader is malicious, this vertex may not exist. So parties prioritize pointing to the leader vertex until some time. And if it so happens that there are 2t plus 1 vertices from round R plus 1 that point to the leader vertex in round R, then at that point I can commit my round R leader vertex. Okay? And this is where I do the step of linearizing, which I do in a very peculiar fashion, where I first find a path to a leader vertex in the largest lower round recursively, and apply the same commit rule recursively in lower rounds. So in this particular example, I will first, when I'm committing the leader vertex of round R, I'll first attempt to commit the leader vertex of round R minus 1, because that is the largest, that is the leader vertex in the largest lower round. And after I have applied the commit rule to that, then I order rest of the vertices. I can order all of the vertices between the non-leader vertices of round R minus 1 and the leader vertex. So and over here you can apply any deterministic ordering that you like.
Is this ordering rule new for Sailfish, or that's standard for that?
It's what all prior works did as well.
Okay.
Go ahead.
So I guess I'm just wondering, how does it compare with Ethereum? Like, as Joachim told me, Ethereum is like the block proposers are distributing their blocks using some diffusion protocol, and the consensus is only on the metadata already anyway. So like, if the consensus is just on the metadata, like, does this have any advantage over Ethereum's approach?
I think the question that you're asking is very broad, so I would prefer to take it at the end, if you don't mind.
Because it seems to me like at a philosophical level, this is just doing distributing the blocks in a distributed way and running consensus on some metadata.
That's
And
right.
that is exactly what Ethereum is doing. So why is like DAG particularly?
That's right, but I think I would prefer to maybe I think the thing is, I think we can devolve into a long discussion on that. So I think I'd prefer to take the question at the end. What happens if your round R leader is Byzantine? Okay. So due to RBC, equivocation is not possible, but it may so happen that your round R leader vertex is not delivered. Okay. If this happens, what we require is that parties send, either they point to this leader vertex of the previous round, or if they cannot after this timeout, then they send a no vote message to the leader of round R plus 1. Okay? And what we require the leader of round R plus 1 to do is the same thing. Either you point to a leader of round R minus 1, or you show a certificate of 2t plus 1 no parties. So 2t plus 1 parties are saying that they cannot vote, and that justifies not pointing to the leader of round R minus 1.
Can the votes be split? That some people vote for no vote, other people vote for the leader, and neither gets the threshold?
No, I guess it will so turn out that will not happen.
Okay, then you will require some double voting, right? Even though I voted for leader, I'm going to vote for timeout.
Yeah, I think so. Byzantine parties can do that, but honest parties will not do that.
But then you will have split votes, right? Neither reach the threshold, no?
So I think let me go through the safety argument. I think I'll go through perhaps exactly that. So the core of the safety argument is the following. Let's say some party commits a round R leader vertex V. Okay, then what we are going to argue is that any commit that happens in a round R prime greater than R, okay, so that leader vertex will always have a path to this round R leader vertex V that was committed earlier. Okay, so why is this? Why does this claim kind of capture safety? It's because of a commit rule. In a commit rule, we say whenever I want to commit something, I'm going to recursively go to lower level leader vertices. Let's look at the base case where r prime equals r plus 1. Over here, observe that there are 2t plus 1 votes from around r plus 1 on around r leader vertex. This implies that at least t plus 1 of these are honest votes. Okay. This implies that if they have pointed to the leader vertex, there cannot exist a quorum of 2t plus 1 vertices who do not point to the leader vertex. Okay, and hence a no vote certificate cannot form. The more general case where r prime greater than r plus 1, let's look at r prime equals r plus 2. Over here, I'm going to look at two different quorums. One is the quorum of parties in round r plus 1 that have voted for the leader vertex of round r. And second, observe that in round r plus 2, every vertex, including the leader vertex, points to 2t plus 1 vertices in round r plus 1. So the intersection of these two quorums contain t plus 1 vertices, and this ensures that there is a path from r plus 2 leader to the round r leader. So the argument for r plus 3 and so on, it's a little different from this, but it follows a similar pattern. So let's look at the latency. I'm committing a round r leader vertex in round r plus 1. Observe that every vertex over here is 1 RBC time. So this implies 1 RBC plus 1 RBC. But something that I did not mention earlier is that for the second round to actually commit, you actually don't need to finish off the RBC. You can actually commit this based off of the first messages that you receive in the second round. So that's why the second RBC, for the DAG protocol construction, you need it. But from the standpoint of committing something, you can do it based off of the first message of the RBC that you receive. And that's why your leader vertex can be committed in time 1 RBC plus 1 delta. So this was the key latency improvement over prior work, Shoal and Bullshark, which required at least 2 RBCs.
So you're saying this is specific to Sailfish, this step?
Yes.
Okay.
Wait, sorry. I have. Is this better than like linearly ordered log in terms of latency, or?
So I think my talk is in 3 parts, and the second part of my talk will answer that question.
But the non-leader vertex latency stays the same. So why is it useful to improve the leader vertex?
So non-leader vertex latency is 2 RBC plus 1 delta.
Yeah.
Earlier it was 3 RBC.
Oh. But
So-
still, my question is, why is it important to distinguish leader vertex latency and non-leader vertex latency?
Oh, it's so I think it's perhaps not. Again, I think part of it, I think this is where I guess my views have evolved over time, and this is the chronology I was referring to. So this is how I thought of it, and I'll tell you, I think perhaps when I go to the second part of my talk, I will say perhaps we should just talk about the worst case latency, and at that point, we should only care about the non-leader vertex latency, because that is the worst case that matters, right? That with the queuing time. If I were to compare this to the state of the art, I mean, the way we usually do it in academia, if I compare this to prior work, let's say, let's compare protocols with the same communication complexity. So if I'm looking at the competing work, the prior work Shoal, so it can be instantiated with communication complexity n cubed, where both of these protocols use RBC. And RBC over here that we use is the one by Daxiang and Ling. And this allows, so this RBC requires 4 delta time. So prior work required 8 delta latency. Our work could do it in 5 delta latency for the leader vertex. And then there's an appropriate addition for the non-leader vertex. If I were to use the fastest RBC that exists in the world with signatures, that's by Abraham et al. At that point, your RBC requires 2 delta time, and that's why our protocol can commit with time 3 delta. Okay, comparing this with this other work, these couple of works called Cordial Miners and Mysticity, which opened up the RBC black box to improve latency. Even compared to them, we improve upon their latency. Okay, so they are not modular in the sense that they do not rely on your RBC black box. How can we observe this latency advantage in practice? So we did experiments, we compared it to prior work where parties were distributed equally in 5 different regions, worldwide, US East, US West, Europe North. Tokyo and Sydney. And here are the graphs that we see. Over here, the x-axis is throughput, y-axis is latency. And we are comparing this work to prior work, Scholl and Bulshak. So you want higher throughput and lower latency, so the lower and to the right is better. And this basically confirms that whatever we showed in theory, it matches up in practice. And over here, the code base that we used is exactly the same. So this was an experiment with 10 parties. Even if we grow the number of parties from 10 to 50, similar parameters hold. So at network size up to 50 that we experimented, the latency improvement still exists.
Are any of them being used in practice? Like these are real-world protocols, or they are academic papers?
So these are academic papers that I think at some point Scholl was going to go into production, but it did not, because I guess they put some other protocol in production.
Which company was going to use?
So at some point Aptos was going to put Scholl in production is what I thought, but I guess they have an improvement over it called Raptor, which I think they will put in production at some point.
Is it still DAG-based?
So Raptor is not, but Mysticity, which is DAG-based, is in production with SUI, and that is DAG-based, yes.
Why does latency go up with TPS?
Why does latency go with TPS? So the intuitive reason is that when you're sending blocks, when you keep receiving more and more transactions, your blocks are larger and you're transmitting more data.
But shouldn't the ping time dominate the additional small
At some
time
point it
time?
does not. So until some point it does, and after that it does not.
So is it purely for network reasons during latency, or is it the compute at that TPS is what starts to dominate?
I would say it's a combination of the two, but the network definitely matters.
And you don't even have an execution layer for these experiments, right?
No,
It's just, yeah.
there's zero execution.
N to the 4 communication, is it per block or is it in total?
It's the communication in a given round.
In a given round, I
So
see.
if you amortize it, you can reduce and
to
reduce it.
N of to N to the 3 if they're all
Yeah.
proposing or something.
Yeah.
But that's still higher than non-DAG protocol, right? N to the 3.
Yes.
So here, my takeaway is that you have a throughput gain, right? But latency gain seems small, because latency gain should apply even when throughput is very low, right? So or are you saying that difference between 2 seconds and 1.7 seconds is the delta, is the effect of shaving off deltas?
I think that is what we see in practice, yeah.
So I don't understand the configuration. How do you make the throughput bigger? Is it like you just send more, make the block size larger, or?
So I guess in general with DAG-based protocols, right? I think the reason why you get better throughput is because you don't have just one party disseminating, you have all n parties disseminating at the same time. And because you have all n parties disseminating at the same time, you're utilizing your network bandwidth in a better way.
Well, my question is about what knob are you turning to make the throughput bigger? Are you putting in more nodes, or are you making the block size bigger too? Because your curve is a trade-off
So
between
over
latency
here,
and throughput.
what we do typically in these experiments is that for a given load, you try to optimize your block size in such a way that you can get the best possible throughput. In such a way that you can manage the load and you can keep your latency to as small as possible.
So all of these points are the same number of nodes, right?
Yes.
Okay,
So all
so
of them are with 10 nodes.
With 10 nodes, and you're just changing the block size essentially to get these points.
So I guess what is changing is the number of transactions that you're receiving. Yes. So your block size may change, yes.
Since there are multiple proposers in the same slot or in the same round, it's going to be a dirty throughput, right? At the end of the day, because you might have multiple proposers, including the same transactions.
Yes, I think this is an overall drawback with DAG-based protocols, where different parties can send the same transactions. Yes, that is true.
Can you go back to previous slide again? So at some point the latency should go to infinity, right? Is it
Yes,
if
that
it
is the
saturates
infinity point.
Okay, so that is the point that it goes to infinity.
Yes.
I see.
I mean, after then you stop, right?
But hold on, I'm still confused. Why is the latency so long? Like, is most of the time on the ping latency or just the network bandwidth? Is like the network bandwidth the bottleneck here?
Network bandwidth is the bottleneck. So remember, we are putting it in 5 different regions, and that includes Tokyo and Sydney. And the ping latency over there is something around 250 milliseconds.
But then latency is the bottleneck, not bandwidth, not network.
Latency is the
bandwidth.
bottleneck, yes.
Wait, I think that means bandwidth is the bottleneck. Like, it's not the number of rounds. Is it the number of rounds, or is it the time it takes to transmit this data across the network?
So both of them play a role, right? It's a combination of the two that plays a role. And how does that combination really matter? For that, let me move on to the second part of the talk. Typically, we write these papers and we have these fancy tables. And after these fancy tables, we say, hey, we improve latency, we improve communication complexity. And that is why, these are the parameters where my protocol performs better. And this is why you should be using my protocol. I mean, that is how you would put it if I were to use it in practice. Now, this is, if I'm really thinking about practice, right, I think this is actually what protocol should be used is a very hard question to answer. There are several factors that come into picture. So as an example, Elaine may come in and say, why don't you use Pala or Pili or some other protocol, because I think it will give you the same set of guarantees, right? Itai may come in and say, use hot stuff or use SBFT. Ling may come in and say, use my protocol because it gives you granular synchrony. And if I really have to make this decision in practice, it turns out to be a very hard question on how to compare protocols, okay? So forget comparing protocols. Let's say, we have chosen Sailfish as the protocol of choice for simplicity, okay? Over here, I present 2 variants. Which variant should I pick in practice? How do I make this decision? So for one, we optimize communication complexity and latency in terms of number of rounds separately. The way they interplay with one another is something that we do not think about as much.
I'm still confused.
Right?
Like, in the previous slide, when you say the cost is it quadratic or cubic? Is that just the metadata cost, or is like, are you treating the block and the metadata the same? Because it seems like to transmit the block, that's just quadratic, right? Everyone sends it to everyone else.
So everyone sends it to everyone else, but there are quorums of messages that you're sending as well. Every party sends a linear, so every party sends these certificates to everyone else as well, and there are n other parties that are doing that.
That doesn't depend on the block size.
So over here, I'm imagining a constant block size. So at that point, it is n to the 4.
Maybe you're saying that every time you're pushing n square bits, right? Like basically every proposer.
You can optimize the block
but I'm
size
saying
with
that's
respect to n.
to get these
Yeah.
bounds, right? So you're
Yeah.
trying to commit n square bits,
Yeah.
and then you either pay
So,
n to 4
so this is
or
the
n to-
communication complexity for a given layer.
You're trying to
which,
commit.
which commits n square bits.
Sure.
That gives you the throughput.
Why is it
Sure.
n squared? There are n players, and each player has 1 bit. Then
No,
n.
no, order n. So each player in this, to make this optimum, like these each player has like an order n message.
You mean each block size is n? Should I think
I don't
of
know
each?
what a block size
Or
is.
even
Yeah.
the metadata alone is n, you're saying.
I mean, just taking all the hashes of all the links from everybody else is an order n thing, right?
So I
Doesn't
mean,
make- the metadata is order n. Yes, exactly. So just the
Well,
DAG.
that I think we shouldn't assume upfront metadata is n, because there may be protocols that allow you to compress this information, like threshold signatures and stuff.
Okay.
I think it's better to like.
so Elaine, should you use threshold signatures in practice? Let me ask you that question.
Should I what?
Should you use threshold signatures in practice, right? I think that's a difficult question to answer.
But this table is like a theoretical table, right?
Sure. So I think over here, this table is talking about the communication complexity for a given layer, assuming fixed size data. So it's talking about all of the different n's that could exist. So there are n parties, each of them who are sending a linear number of linear amount of data just in terms of the metadata, and you're passing it through an RBC, which at least takes n squared time.
there's something I find a little strange here. So if I understand correctly, you're saying one major motivation of DAG protocol is to balance the work in a more natural way, right? Even though leader-based protocols can do that using erasure code. But now you're using RBC. I think that's my CCS paper from 21. But that RBC uses erasure code. Right?
Yes.
So then
So
this doesn't, right?
sure, but again, I think us as theoreticians, that is what we would do.
So
Right?
in
In
reality,
practice-
we're putting an RBC that doesn't use erasure code?
In practice, yeah, I think that is what I would want to go. In fact, I think what you would want to do is you would want to think about some sort of an optimistic path where you just do a consistent broadcast instead of a reliable broadcast. So, for example, I think if I'm not wrong, in the paper, I'm pretty sure in production code as well, in Mysticity, that is what they do. They just do a consistent broadcast, and if you need a message, you ask for it after the fact. And that is how you save complexity over there. Okay, so coming back, I guess, which of these protocols should I pick is a hard question to answer. So what are the different things that come into picture? One is communication complexity and number of rounds. How do they interplay with each other? A second question that you may want to ask is, how does computation affect performance? Are there any complicated crypto operations involved? Third, how does an adversary affect performance? And your adversarial behavior can change, depending on the protocol itself, and its effect on the protocol can be dependent on the protocol itself. Fourth, your ideal protocol can actually change with your changing n as well as changing load or load in terms of the number of client transactions that you receive. And finally, how much does it really cost to run these protocols in a deployment? If I were to take this protocol and go out and practice and use it, there are so many questions that we need to answer before we figure out what protocol I should use. And different projects, right, that we know of, they kind of make different trade-offs in what they think is important. One project, as in the process of advising Espresso Systems, this is one project that I was working towards, where Espresso Systems, together with Off-Chain Labs, they want to implement what is called as a decentralized time boost sequencer. Okay, so they have a very specific requirement on achieving this decentralized sequencer, but at its core, what they need is a state machine replication protocol. And if you look at their goals, the key goal that they want to achieve is good latency. So far as I can get this latency, they're willing to trade off a lot of different things to get good latency. In addition, they want other parameters like you want MEV protection, and for that, some of these transactions could be encrypted, and after you agree on them, you would want to run a threshold decryption to decrypt them. Okay? They require some other things as well. For example, there is a priority lane controller which prioritizes some transactions, right? So these are their requirements. Let us try to see how these requirements map to the questions that I asked. So they're interested in achieving low latency, and for that, they're willing to go for a very small n equals 13 or n equals 21. They're willing to tolerate a very small load. We are not talking about 200,000 transactions a second. We are talking about 1,000 or maybe 5,000 transactions a second. They want to ensure that, since latency is a goal, they want to ensure that failed leaders, they should not have an effect on your performance. And finally, they want to have support for encrypted transactions.
So actually, so for this Espresso system, I'm just curious, like they're using a DAG-based protocol to do this?
So this is separate from what Espresso Systems is doing for their confirmation network. So this is like a separate collaboration between Off-Chain Labs and Espresso Systems.
Oh, so like, I guess someone told me that they're no longer working on the decentralized sequencer. Is that true?
I think I'm happy to discuss all of this, but I think so. This is a decentralized sequencer for Arbitrum, potentially for Arbitrum.
And they're trying to use DAG, or they're not trying to use.
So they are using DAG, and they are using Sailfish, in fact.
Oh, okay, that's pretty cool. Yeah.
Yes, but I think for their confirmation network, no, they are not. They have a leader-based protocol. So these are like two separate things. So when I'm given all of these options, right, the typical thing that we do is we look at all of these protocols, and intuitively we try to argue maybe this protocol performs well, maybe that protocol performs well for so and so reason. And we have intense discussions, and then we figure out, this is the protocol we should implement. So our approach, if you look at it, is to say, hey, we want to optimize number of rounds, and we want to optimize the communication complexity. That's our typical design goal. So we have protocols with O1 rounds and poly n communication complexity for some small poly. Once we have that, we implement these protocols. Then we run experiments on top of it, and then we hope that they give you good throughput and latency. We optimize one thing, and we hope to get good guarantees on something else. And in practice, this may not always yield ideal results. An example over here are DAG-based protocols, where at least in practice, I think we can figure out why at some point, but at least in practice it was shown that when n is small for moderately sized settings, for n equals 100, you can actually get good throughput even if your protocol has high communication complexity. So we are in this world where we are optimizing for something but hoping something else gets better. Okay? And in between this, we have a lot of development cost and a lot of cloud costs in terms of running these experiments themselves. This next work, it's trying to address exactly this question. How do communication complexity, number of rounds, different n, different load, how do they interplay with each other? For this, we have this new work called the pipes model for latency and throughput analysis. And this is not a new protocol, it's just a way for analyzing existing protocols. Okay? So the goal over here is to analytically, and I stress analytically, compute the trade-off between throughput and latency for a given protocol that's running with a given number of processors or a given number of parties. Okay? So you have a set of n parties, each connected with each other with a delay of delta. Okay? And there is a bandwidth S for every party. Over here we think of time as being in terms of number of time slots, where you can think of time slot as an infinitesimally small amount of time. Your bandwidth S is in terms of number of parcels, packets, chunks of per unit time. Okay? And the entire system receives transactions at the rate of some d packets or d parcels per time slot. So what we are trying to get at is, how does latency relate to d when you fix an n, when you fix a delta, and when you fix an s?
Sorry, so S is the total bandwidth to me, or per chain?
Bandwidth is per party.
Per party, got it. Incoming, outgoing?
We assume it's the same thing. So all of those can be tweaked. This is like the first work that we did. So we are actually making many simplifying assumptions over here. We assume synchrony always holds, because in the good case that is what happens. In fact, we assume that there's an exact delay delta in between any two parties. We assume all parties are honest, as well as we do not consider computation time. And under this scenario, I think we are trying to ask, what is the worst case latency that I get under the best case conditions? Best case conditions meaning all of these guarantees holding. And worst case latency is from when a transaction arrives until all parties have committed. That is the overall latency we are considering for a transaction.
What is the worst case over at this point?
So I think one thing that plays in is whenever a transaction comes in, it can get into a block immediately, or it may have to wait for some amount of time for the next block to be produced, for example.
So it's a stochastic arrival process, you're saying? Or?
Yes. So you're getting transactions at the rate of d packets per time slot. So some transactions come early, some transactions come late, and we are looking at just the worst case time. So I'm actually not going to get into the details of how we do this, because my co-author Andy is going to give a full talk on this. But since I'm talking about Sailfish, I'll show you the result of what we get if we apply our model to Sailfish. Okay? So we get an equation of the following form, where latency is given by this expression. Over here in this expression, again, n is the number of parties, s is your bandwidth, lambda is the size of a size of a vote, size of a hash. Delta is the delay between parties, and d is the transaction load.
D is what?
The incoming rate of client transactions.
Can you go back to the model again? I'm still confused.
So d is the rate at which client transactions are arriving at the system. Okay, so this is the effective throughput that you're going to get.
And bandwidth is like the total bandwidth to.
Bandwidth is the bandwidth of one party. So if I'm running a processor and if I'm running an 8 Gbps network, then my bandwidth S is 8 Gbps.
So can I assume the network is everyone has, let's say there's a trusted authority that has infinite bandwidth and everyone has a bandwidth S linked to that trusted authority? Should I think of the network as that?
So yes, I think I'm assuming that you get a fixed bandwidth from, if I'm using an AWS machine and if AWS tells me it is going to give me 8 Gbps, then I'm going to trust that I'm going to get 8 Gbps. Yes.
And you are assuming if I need to talk to multiple parties, how to divide the bandwidth between them?
I mean, for most protocols, you divide it equally, but you could have protocols that divide it in a different way, right? So at the end of it, when I receive a machine from AWS, it tells me this is the bandwidth. It does not tell me how I should be using that bandwidth. If a protocol uses it unevenly, they can. That's okay. That can be captured when you're analyzing it.
But isn't that just this? Is that different from the standard model? Like when we work on linearly ordered log, isn't that also the same model?
It's the same thing. When you get a machine, you have some bandwidth, right?
So this is not a new model. It's just the standard model.
So we are trying to capture the existing model, I think, as faithfully as we can, while making a lot of simplifying assumptions because we are doing this for the first time. Go ahead, Pranav.
So in the model, everybody is the same S, or are people different S's?
We are assuming the same S for everyone. Yeah, we are assuming the same S for everyone. We are assuming the same delta for everyone as well. Which in practice in a geo-distributed setting, that's not true because US East and US West are much closer than US East and Sydney, for example.
I guess my question is like under this model, assuming the protocol is load balanced, let's say it uses those diffusion protocols that Lin is talking about, then the bandwidth should be indicative of the throughput, right? The total bandwidth consumption. I mean, assuming the protocol is automatically load balanced.
Yes, I think that is what this, so after it is load, so with Sailfish, it's already load balanced. And when you analyze it, it is, okay, think about it in the following fashion, right? You have transactions coming in at a given rate, and the protocol has to take these transactions, put them in a block, and send them over to everyone and run your protocol. So you want to ensure that your protocol can tolerate this incoming set of transactions. That is, by the time I process one block, the number of transactions that arrive in that time frame, it should not exceed my block size, because if it does, then my latency shoots up. Right? So assuming that is what is happening, that is, we are setting the block size in that fashion, we can analyze this and you get the corresponding latency metric, latency equation that you see over here. For this particular latency metric, over here, as I mentioned, fixing delta, fixing S, fixing N, and fixing lambda, you're getting a relationship between D and latency. Okay? So one thing to observe over here is that if D is much smaller than S, if you look at the second term, there is an S over D term over there. At that point, S over D is very large. So that makes the denominator very large, and that makes the second term 10 to 1. Okay? So your latency is entirely defined by the first term. As D approaches S, S over D is very close to 1. If S over D is very close to 1, the denominator is very large, very small, and at that point, the second term tends to infinity, and your latency tends to infinity, which you typically expect. So if I try to plug in parameters, in a geo-distributed setting, these are some arbitrary numbers that I picked. Delta equals 200 milliseconds, N equals 400, picked an S, picked a transaction size. If you plot it, this is the curve that you observe.
This is an upper bound, or this is exact in your model?
This is exact. This is like a fixed equation, so I'm just plotting the equation.
Right, but as far as the analysis that leads to the equation, is it an upper bound on latency in your model, or is it kind of exactly what it is?
So we fix everything, right? So I think we are saying it takes an exact delta amount of time, for example, for data.
Sure, but you do a bunch of math, and like the math could be tight, or the math could have like.
Oh, I think it's tight. I think we keep it tight.
Okay.
Yes. Yeah.
So what I don't understand is if D goes to infinity, I think the latency should be unbounded, but in your expression, the latency doesn't seem unbounded when D goes to infinity. Because if the rate of incoming transaction is arbitrarily large, then most of the transactions will never get confirmed, right? So the latency should go to infinity.
So I guess in our analysis, we consider, so I think the way we set our block size is in such a way that you can tolerate. So I think what we do is we say we're going to set a block size. I mean, again, I think this caveat that you mentioned, I think we write it in the paper. So we set the block size in such a way that the block can be cleared and the number of transactions that arrive by that time is fixed. So there exists, so I mean, in terms of the analysis technique, right, we ensure that there exists a time where there are no transactions at that party. So I think there is, I mean, what you're suggesting is like a trivial bound, which we do state in the paper.
But I mean, to relate Elaine's question to the formula, I mean, I think that is only that's only defined for D less than S, right?
Yes, yes.
And then as D approaches S
Yes.
from below, that blows up to infinity, as you were suggesting.
Exactly.
So as D
As
approaches
S from below, right? Then S over D approaches 1, so S over D minus 1 approaches 0, so that last term blows up.
I see. So it's assumed D is less than or equal to S.
Otherwise,
Yes.
this doesn't make sense, yeah.
Exactly.
Right.
So like intuitively, like as long as like when D is small, like latency should be only ping time, and like in
Yes.
a certain regime, it feels like it should be like flat, and then at a certain point, the like block size starts to affect.
That is
things.
exactly what you see over here.
Like why is the left even the curve? Why isn't it like flat and like actually
Oh, it's
a straight
because
line?
this second term is not really 1, right? It is something a little bigger than 1. As
Right.
D keeps increasing,
Yeah,
it's a-
so I guess like it's clear from the equation, but like is there an intuition of why it's bigger than 1?
so the intuition is that your block size, as D increases, your block size has to be larger and it takes a longer amount of time to disseminate it.
I guess like as long as D fits in the pipes, it's unclear why that would be.
I mean, so whenever you're sending some message, right, there are two things that come into picture. One is the ping latency, the capital delta, and one is the latency to actually send this block. So if I'm sending some X bits of data, for example, and if my bandwidth is S, the time it takes for me to send it to every party is X over S, right? If X is large, so the total time is X over S plus delta, for example, right? So if X is large, then this total time keeps increasing. And that is the effect that you see in a larger block size, and that contributes to it.
Another question, what I find confusing is people typically cite DAG as improving throughput, but your point is it's actually improving latency rather than throughput.
I mean, it's just a trade-off. I think my next slide is going to ask, does DAG really improve throughput? Or, I mean, does DAG really improve throughput or latency? So, I mean, this example over here, I mean, I'm going back to the question that I asked. For decentralized time boost, we said we want a small n equals 13 or n equals 21. If I were to take that setting of n equals 13 and plug in delta equals 200 milliseconds and s equals 10 Gbps, over here we have a corresponding plot for Sailfish, and I also compare it with a leader-based protocol that actually uses a communication efficient way using erasure codes, and that is dispersed simplex. And if you look at the curves that you see for both of them, you can see that dispersed simplex can actually do better in this particular setting.
Why is that not a smooth curve? Why does it shoot up like that?
I mean, the exact equation, if you see, I think you'll see that that happens. So if I were to run the same thing in a single region, in a single data center, at that point, you know, your delta is going to be small. Delta is going to be 20 milliseconds, let's say, and if you have a smaller bandwidth, then the story is even more different, where, you know, until some point, until some throughput, Sailfish is better, and then simplex starts becoming better, and eventually, you know, Sailfish starts performing better again. So in the third part of the talk, I think I'll not get into it, but let me just tell you, I guess, what the result is, or what we are doing. So I think the question that we ask is, you know, whether computation affects performance, and, you know, how much does it cost to run a protocol in deployment. One, we want blockchains to be post-quantum secure, and second, if you look at deployment costs for, you know, all of these protocols, they're very expensive. So all of these protocols are running on 32 core machines, and if you look at the DAG literature, newer protocols actually use more cores for various reasons, you know, one of them being, you know, verifying signatures. So these protocols are very expensive, and the question we asked was, you know, can we run these protocols on a 4-core machine. And our work, optimistic signature free reliable broadcast and its applications, addresses this question. So it has, the core of it is an optimistic latency reliable broadcast protocol. And once you have that, you can get several other protocols and we can obtain signature free Sailfish. So this part is where I was about to explain how can you make Sailfish signature free. So the first part is you can rely on BRCA broadcast. In fact, you can do something better by going over an optimistic 2-round reliable broadcast protocol. And the second part where we really rely on signatures, you can sidestep that using a simple trick where instead of having a no-vote certificate, you directly point to vertices of round R. So do signature-free protocols work well in practice? We ran this on simple 4-core machines, and we observed that they can perform better compared to signature-based protocols under specific settings. And there are some nuances in running regular BRCA as your RBC versus an optimistic version of BRCA as RBC because of the number of regions involved in these protocols. So before ending my talk, a shout out to my collaborators, especially Nibesh, who's a risen star in this space, and look out for exciting work by him. And here are all the papers that I spoke about in this talk. I'm happy to answer all questions after the talk.
So from talking to the Solana people in practice for things like Rotor, they seem to say that the time it takes to actually send things out is negligible compared to the ping time. And that seems to be a bit different from your models. So would you say that's a misunderstanding, or?
So when you say it's negligible, at the end of it, our model captures it in the cleanest way possible, right? There is a bandwidth and you can send data only at a given rate. You can't send any faster than that, right? No matter what you use to send, that much amount of data has to go out, and you cannot cross physical limits in a sense, right? So the only thing we can do is take their protocol, analyze it, and see why they get good latency.
I would speculate that the rates at the Solana validators is quite a bit higher than the ones used in these experiments. So what looks non-negligible here maybe looks negligible if you have got that kind of hardware. That would be my guess.
So so it can be hardware, it can be the amount of data you're sending as well, right? If you're looking at, for example, sending 1 kilobyte of information over an 8 Gbps network, and if your ping latency is 100 milliseconds, at that point, that is really small compared to 100 milliseconds. But instead of 1 kilobyte, if I'm sending 1 gigabyte worth of information because I want to have high throughput, that argument is different.
Can you go back to the formula for Sailfish?
In some sense, it says that as the hardware gets better, right, you can get better performance, which is kind of what we want, right? If you can get better throughput for your bandwidth, then you can get better performance.
So I assume the first term, the 7 lambda n squared, that's roughly speaking the communication complexity, right? You divide that by the bandwidth plus 7, I assume that's the rounds, right? But doesn't that mean the two traditional metrics, rounds and communication, indeed are good indicators?
So again, I actually had this slide which I removed because I thought my talk was too long. So these are good indicators. They do not completely define, the performance.
But what's the intuition why? I feel like these should define the performance in your network model, because I thought you have a new network model, but actually the network model is the same as
So Elaine, let me give you maybe some counter arguments, right, to what you're saying. If these metrics are indicators of good performance, then hot stuff should perform better than Tendermint under all circumstances, right? What we show in our paper is that is not true.
But that one is not balanced, right? So if it is balanced, then
perhaps
what more?
Yes.
So, but what is the reason why hot stuff is not as performant as Tendermint?
I'm saying hot stuff is not better than Tendermint. So although it has lower communication complexity. And if you think about it, the reason why it's not as performant is because if you have all-to-all communication, you incur 1 delta. If you're passing these things through the leader, then you incur 2 delta. So in that sense, it is worse. So you're paying deltas and you're improving communication. Okay, and the communication improvement is not buying you much, but paying deltas, you're worsening things.
When you say better, there are 2 dimensions to there's throughput and there's latency, right?
So
like, it sounds like it should have better latency than Tendermint. Otherwise, it seems like it's counterintuitive. I mean,
I think
if
that is the point I'm
communication-
trying to make, right? It is counterintuitive. It feels counterintuitive, but you can actually reason about it. So you can actually figure it out that both of these metrics, if you plot these curves, which we do in our work, you will see that one is better than the other.
But I think there should be a more straightforward. If it is worse, there should be a better explanation.
I'll try to ask Elaine's question because she's assuming we already have assuming a balanced protocol.
Oh
Can
yeah,
I-
I'm assuming balance.
Yeah. Can I then just take my communication, divide by s plus the number of rounds? Is that
For the most part, I guess that is what is happening with dispersed simplex. And I guess the diff that is dispersed is balanced, right? And that is kind of what is happening with dispersed simplex. And what you see over here, this gap, is that factor of 3 that you incur when you're doing erasure codes.